My name is Aparna Bhooshanan, and I'm excited to share my research project with you today. This year, I'm working with Dr. Ahmad Alsharif and Dr. Chris Crawford. Our project's title is BlockCrypt, a block-based programming platform for modern cryptography. I began working on this project this June, where I programmed the BlockCrypt application. Tonight, I'll be sharing BlockCrypt's background and the work that I've prepared this semester. To start, I will offer a general overview of some relevant cryptographic concepts. Cryptography is the science of designing mechanisms that achieve many goals, including confidentiality, which conceals data so that only the intended recipient can see it, data integrity, which ensures that data remains pristine and authentic, entity authentication, which verifies a user's identity, and origin non-repudiation, which ensures that a party cannot deny their participation in a transaction. We can use various cryptographic techniques to achieve these goals. For example, public key encryption achieves the goal of confidentiality. Hash functions can achieve the goal of data integrity. Authenticated encryption can achieve both confidentiality and integrity simultaneously, and so on. Advanced or modern cryptographic techniques are represented in our daily lives in many applications. These applications include anonymous communication, where users communicate without revealing their identities. Another application is multi-signature, where multiple signers must sign a single document. A real-world example of that is DocuSign. Another application is anonymous digital coins, which are a type of cryptocurrency that conceals transaction details. Finally, we have encrypted search, which keeps user queries and results private. Next, I will offer some context surrounding K-12 cybersecurity education. This research project's main inspiration comes from Percival et al.'s paper entitled CryptoScratch, Developing and Evaluating a Block-Based Programming Tool for Teaching K-12 Cryptography Education Using Scratch. The authors identify a worsening dearth of cybersecurity professionals in a world of increasingly sophisticated cybercrimes. Yet, despite the situation's direness, and despite governmental, academic, and industrial attempts to raise awareness surrounding cybersecurity among children, only 5% of high school students and 1% of middle school students are even aware of topics such as cryptography, which is a crucial aspect of cybersecurity. In response to this issue, the National Security Agency has created resources for students to encourage interest in cybersecurity. However, because of a lack of hands-on practice available to these students, such programs are generally limited to teaching very simple concepts such as the Caesar cipher. Another critical part of our research is the concept of block programming. Block programming is an introductory visual programming approach that allows users to drag and drop pre-programmed blocks. This offloads the burden of remembering syntax, keywords, and other programming concepts from beginner programmers, allowing them to focus purely on the logical concept of programming instead. Prominent examples of block-based programming languages are Scratch, MIT App Inventor, and Blockly. To the left, we have a simple block programming example that prints "Hello World." This leads me to our first research question. How can block-based programming be extended to teach advanced cryptography concepts while remaining accessible to learners with little to no coding experience? A technology that attempts to answer this question is CryptoScratch, the creation of the researchers I mentioned earlier in this presentation. CryptoScratch is an extension of the block programming language Scratch. It was developed by Percival et al. To implement modern cryptographic algorithms, such as AES, RSA, and SHA-256, as programming blocks. This approach allows students to focus on understanding the mathematical premises behind cryptographic algorithms. To the left, we see a diagram illustrating the basics of an encryption and decryption algorithm. For encryption, a message M is encrypted using a secret key K, and the output is a ciphertext C. For decryption, an encrypted message C is decrypted using a secret key K, and the output is a decrypted text M. To the right, we see the CryptoScratch representation of the encryption and decryption technique that I just described. The blocks allow beginner users to visualize and interact with each variable. CryptoScratch is advantageous because Scratch is a programming language that most students can pick up rather easily. It is arguably the most popular block programming language, and it is free, which implies more equal access to it, and it also lowers the barrier to entry for cybersecurity education for young students. Scratch is perfect for introductory cryptography because basic cryptographic functions are especially easy to represent in a JavaScript environment, which is what Scratch is based on. However, it does have a few limitations. These include the fact that they are limited to simple cryptography primitives, such as AES and RSA encryption, or SHA hashing. CryptoScratch cannot support modern cryptographic algorithms that rely on complex mathematical operations, such as attribute-based encryption. Some examples of attribute-based encryption include setup, encryption, key generation, and decryption, which are all very complicated algorithms that are inaccessible to CryptoScratch. Additionally, game-based learning scenarios for modern cryptography are similarly unexplored by CryptoScratch. This leads into our second research question. How can we design a block-based programming environment that supports modern, computation-heavy cryptographic algorithms using real cryptographic libraries rather than simplified browser-based primitives? To address the research questions, I am developing BlockCrypt. BlockCrypt is an application that uses Google's Blockly library to extend CryptoScratch's functionality. It supports more advanced, modern cryptographic algorithms. Furthermore, in the future, we plan to implement game-based scenarios for modern cryptography learning, such as capture the flags and puzzle-solving games. This diagram illustrates the architecture of the BlockCrypt application that I'm programming. The Blockly frontend interacts with Electron, which in turn interacts with the Python backend. At runtime, the crypto library is loaded, and the result is printed to standard out. In the current version, BlockCrypt supports symmetric key encryption through AES, asymmetric key encryption through RSA, hash functions such as MD5, SHA1, and SHA256, and digital signatures including RSA and ECDSA. Pictured here is the actual BlockCrypt interface that I programmed with an example of asymmetrical RSA key encryption represented with programming blocks. Finally, I will share the project's next goals. In the future, we plan to deploy the BlockCrypt full application using the Charm cryptographic library and the Electron bridge shown in the previous diagram. Next, I will complete the Python backend before adding more modern cryptographic primitives such as attribute-based encryption, proxy re-encryption, linear secret sharing, and group and threshold signatures. Finally, I will program game-based cryptographic scenarios for the application. That concludes my research presentation. I'll now be taking any questions.
Are all the environments, your own included, that you summarized as well, are they working only in the local machine context, or are they able to allow multiple web instances across different computers to communicate? What I'm getting at, it'd be kind of cool for the children maybe to do some kind of cryptographic thing where they're communicating somewhere else. So does that make sense in the context you're looking at? And have you seen anything like that where there's like socket primitives going across different web browser instances with this cryptography capability?
That's a very interesting concept. I don't believe that we're currently planning on implementing that in our research project, but that could be a very interesting future goal.
What are some of the limitations of using Blockly?
So Blockly is a pretty robust language, especially because there are lots of professionals who work on the Blockly team who are constantly releasing new plugins, new extensions for Blockly that are just continually extending Blockly's functionality. However, the version of Blockly that's used in this current beta prototype version of BlockCrypt is too low to actually make use of these plugins. So I anticipate that after we migrate the current prototype to the newer version of Blockly, we'll see some good progress, especially in the user interface, user experience sides of the application.
And why did your research group choose to use Blockly instead of just extending CryptoScratch?
Right, so we chose Blockly because CryptoScratch actually cannot support the modern cryptographic algorithms that we intend to use at all. So Charm, which is the cryptographic library that we intend to use, it relies on Python, and it has heavy dependencies such as pairing-based cryptography, which CryptoScratch just cannot support right now. CryptoScratch itself is just a simple JavaScript-based demo, and it just can't handle pairing-based or advanced schemes easily.
Has your research group identified any possible populations that you would like to test BlockCrypt's efficacy on?
That's a great question. We don't have any specific schools currently that we are targeting for our research, but we have identified a few specific age groups that we would like to provide this application for. So we determined that CryptoScratch's intended age group is probably around grades 4 through 8, whereas BlockCrypt's intended audience is grades 4 through 12. So we intend to target a much wider audience. But more generally speaking, we do intend for the app to be released for the general public to use.